All right, as I was saying, if we have this justice, then I'm talking about set of integers. But once I write z and I put an operation, then it becomes an algebraic structure. Are you with me?
Okay.
So the kind of structure it becomes now depends on the properties that it satisfies. Okay? So first and foremost, for you to be a binary operation, okay, it's some texts and some authors automatically put the property of closure on it. So what do we mean by closure? Closure means if we take two elements of that set and perform the binary operation on it, then the answer will also remain in the set. That is, for A, comma B in the set, in this case, we're talking about Z, A asterisk B is also in Z. Are you following?
Yes, sir.
So some people add it to the definition of binary operation, which is more common, while some people leave it out. So in addition to all of this, we now have some other axioms, some properties that we can look into. Okay, so in this case, our asterisk is particularly addition. Okay, so if I consider Z with addition, this is not just a set, but a structure that has been endowed with a binary operation that is addition. It is definitely closed. Do you understand what I mean by the fact that it is closed?
Yes, sir.
What does it mean? Can you explain that to me?
Okay, that means the result of the operation will be in the set.
If I add any two integers, I will also get an integer. That's just what I want to hear. Okay, that's what it means for you to be closed. Okay, so in addition to being closed, so the fact that it is closed, I can just call it a groupoid, a groupoid. Then in addition to that, if it now satisfies this property one that is actually associativity. Property one is associativity. So if the structure, that is the set together with the binary operation, is closed and the property of associativity is satisfied, then it has graduated from being an ordinary set. It has graduated from being an ordinary groupoid, okay, to what we call a monoid. So, and look at what we mean by associativity. Associativity means we can change the position of the bracket while the operation is preserved. Okay, the answer does not change. Okay, do you understand? So if I have 2 plus 3 plus 7, if the bracket is on 2 plus 3, we are going to get the same answer if we shift the bracket to 3 plus 7. So this is associativity. Okay?
Okay.
So it is true for both addition on integers and for multiplication on integers. Are you following?
Yes, sir.
So that is associativity. Not all binary operations will satisfy the property of associativity. So in that case, the structure there will not be a monoid. Okay, so wait, hold on. Let me confirm if it is actually a monoid or a semi-group. I think I'm using before. Just give me a minute. A monoid. Oh, sorry. So associativity goes with semi-group. Okay. Monoid means it is associativity. Okay.
Okay.
semi-group of G. So associativity means we are talking about, if a set together with a binary operation satisfies the associative property, then we say it is not just a set, it is not just a groupoid, it is a semi-group. Okay?
Okay.
Semi-group. Then, in addition to that, if we have, so I'm going to property number 4 on the list. Okay? If there is an identity. So what is the meaning of an identity? An identity is an element that under the binary operation does not change the element. Does not change the other element. You go and pop. So identity am I represented by letter E. So if I do A asterisk E or E asterisk A, I'm going to get A. Then E is what we call the identity element. Are you following?
Yes, sir.
So if each binary operation has its specific identity element, that is, if that operation has an identity. So if I'm talking about the set of integers, I cannot just ask you, what is the identity element of the set of integers? That question is not really correct. It's not really complete. I must also include the operation I'm talking about. So the identity element for the set of integers under the addition is 0. Okay? Because if I add 0 to any number or I add any number to 0, I'm going to get the number. Are you following? Any problem with that?
No, sir.
But 0 is not the identity element of integers when we are now talking about multiplication. Because 0 times a particular number is not going to give us that number. Okay? So, and that is why we have, so it is stated here, there are 0, 1 in integers, such that a plus 0 equals to 0 plus a equals to a. So it means 0 is what we call the identity element under operation, under addition. And 1 is the identity element under multiplication for the set of integers. Are you following?
Yes, sir.
So, and if a set, which is a groupoid, if it is ordinary set, I will just write Z. If it is a groupoid, it means I have included a binary operation for which it is now, the operation is closed, so it has become a groupoid. Then if a groupoid now satisfies associative property, it is called a semigroup. In addition to being a semigroup, if there is now existence of an identity element, we say it is a monoid. So follow.
Yes, sir.
So from a set, Aposi groupoid. From groupoid, we went to semigroup. From semigroup to monoid. Okay?
Okay, sir.
Then the next one is the property number 5, the identity, the existence of an inverse element. We can never talk about inverse element without talking about identity. Okay, so there can be an inverse element if there's no identity, because what is the definition of the inverse element depends solely on the existence of identity. So what is the inverse element of an integer? So when we're talking about inverse, we also need to talk about the operation we are talking about. So under addition for the set of integers, so for any a in Z, there exists an element that is represented as A inverse, that is A raised to power minus 1, such that A plus A inverse Okay. All right. So let me use the same notations that I used in this material. So generally we use element raised to power minus 1 to represent inverse, but for additive inverses we use minus that element. So for every a in z, there exists minus a in z such that a plus minus z is equal to the identity element. And what's the identity element under addition? 0, isn't it?
Yes.
So the additive inverse of 1 is minus 1. The additive inverse of 4 is minus 4. The additive inverse of minus 7 is minus minus 7, which is 7 itself.
Okay.
0 is also an integer, and its additive inverse is minus 0, which is 0. So 0 is the inverse of itself, which is actually the property of all identity elements. All identity elements are the inverse of themselves. Are you following?
Yes, sir.
So when a monoid, we have the properties that every element has a unique inverse, okay? Then it is no longer just an ordinary monoid, it has become a group, okay? Do you get that? Hello?
Hello, sir.
Did you get that? To get so. Hello, we only have limited time before they continue to the class. So, hello, can you hear me?
Yes, I can hear you.
So, what can we say about a group? A group is a set together with a binary operation, inside brackets, closure properties satisfied, okay, with a binary operation, which satisfies the following property. 1, associativity. 2, existence of identity. 3, existence of inverse. I think that's all. So if we have this, we have a group. If in addition to all of this, we now have property 2, that is a plus b equals to b plus a. Property 2 is what we call commutativity. So we say the two elements commute. So when we reverse the position of the element, the answer is still the same. Okay, then a plus b equals to b plus a. If a group is commutative, then it is not just an ordinary group. We call it an abelian group. Okay. So a group that is commutative is what we know as the abelian group. Is that clear?
Okay.
All right. So the property that is now written in number 3 is what we call the distributive property. Okay? Are you following?
Yes, sir.
That one is not related to a group. That one is actually related to another structure. Okay, because as you can see, there are 2 operations there. The property number 3, yes, you see that there is multiplication, there is addition. So what you call in the ordinary group, group is always a set and one operation. Okay?
Okay, sir.
So, but tabati more 2 operations, what you call in group, what you boss another structure there. So, if I satisfy one properties, then it is called a ring. So, but I don't want to go into that now. But let me just tell you that if in addition to all of this, to the group E, if it now also satisfies this property number 3, that is A dot B plus C equals to AB plus AC, then we say it is distributive from the left. So we call it appoint multiplication from B and C. That's how we call it distributive. Okay? Hello?
Okay.
So this is left distributivity. I hope the noise is not disturbing you. Huh?
No, sir.
Then this one is called right distributivity, because we distribute the multiplication over B and C from the right.
Yes, sir.
So for integers, or basically for almost all number systems, multiplication distributes over addition, but addition does not distribute over multiplication. Are you following?
Yes, sir.
There are some binary operations like that both of them can distribute over each other. I made mention of it the last time. I told you that when we're talking about set, intersection distributes over union, and union distributes over intersection. Okay,
Okay.
but the case is not the same with addition and multiplication. Addition distributes over multiplication. Sorry, multiplication distributes over addition, but addition does not distribute over multiplication. Exactly. Hello?
Yes.
Did you not understand what I said? Take him to so.
More.
Okay, good. So that means we've touched everything here in 1 to 5. But mind you, we only talked about them in addition. Okay? So in terms of multiplication, statement number 1 is correct. So associativity for integers, statement number 2 is correct. So you know when you multiply 2 by 3, it's written as 3 by 2. Statement number 4 is correct. There is an identity. But statement number 5 is not correct. Okay. Do you remember why I said statement number 5 is not correct?
I think you said they will just have 1 and -1.
So not all, it is only one element of the integers that has a multiplicative inverse. Okay.
Okay.
So the statement is not true because the statement says there is A inverse in Z such that A times A inverse is equals to 1. A inverse of A equals to 1. This is only true for when A is 1. Okay, so for example, 2 now, what would be the 2 inverse? 2 inverse is not in Z. 2 inverse is 1 over 2, which is in R. It is not in Z. Are you with me? That is why the set of integers with respect to multiplication is not a group. Okay? Because for it to be a group, there must be an inverse for all elements. Are you following?
Yes, sir.
So it is only a monoid. it is a semi-group, it is a moment, or it is not a group because it does not have an inverse. Okay? So let me ask you a question. When you consider R with respect to multiplication, is it a group?
R. Yes.
Are you sure? What is the identity element?
What is it?
Identity element. What's the identity? Of course, we know that it is associative. Of course, we know that it's there exists an there exists an identity element. What is that identity element? I can't tell you.
I said one.
Yes, well, sorrow with confidence now. So I'm bẹ̀rù báyìí. I'm bẹ̀rù bí ẹni tí wọ́n jẹ sọ. Dúró dẹ̀ ni gbogbo èrò la bá ń bẹ̀. Àmọ́rú yín. So the identity is one. Any multiplicative group, identity is one. But the problem now, you said it is a group. So what is the inverse of, let's start. What is the inverse of 2? Is what?
That's 0.
Is what?
1/2.
Is it a real number?
No.
I can't hear you.
No.
1/2 is not real. What is not real? If 1/2 is not real, what is real?
Rational number.
So really to naturally, so really to 1/2. All rational numbers are real numbers. Just as all integers are rational numbers. Okay? Just as all natural numbers are integers. So 1/2 is a real number. But the case is not the same. I cannot say all real numbers are rational numbers. I cannot go back. So let me clean this equal to Timothy Salem. It is a proper subset. So 2 has an inverse. Kò sí problem pẹ̀lú 2. Kò sí problem pẹ̀lú 5. Kò sí problem pẹ̀lú, even if I write 7/5, what is the multiplicative inverse of 7/5? 5/7. Because when we multiply them together, we get 1. So there's no problem with that. It is looking like it is truly a group. Okay, what is now the inverse of 0? 0 is a real number, isn't it? 0 is an R.
Okay.
But what is the inverse of 0? What will you multiply by 0 to get 1? So 0 is unreal, but there does not exist 0 inverse in R. Therefore, R star is not a group. So yeah. So most times when you are told to check if something is a group, àwọn méjì tó máa kọ́kọ́ lọ nìyẹn. Torí associativity àti associativity and closure kò kí n fi bẹ́ẹ̀ sí problem pẹ̀lú wọn. If it's a problem, is identity and especially inverse. Okay?
Sir?
So to perfect get bóyá nǹkan jẹ́ group or not, ibi tó máa kọ́kọ́ lọ check nìyẹn, then use few examples, very simple examples to see. Is that clear?
Okay, sir.
Good. So we go to the next part, which is talking about
Sir, the question, sir.
philosophy.
Question, sir.
Mi ò gbọ́.
It gave question, sir.
Extra.
Question.
Okay.
You said all numbers are real numbers.
All words?
Rational numbers
Yes,
are
are
real
real numbers. Bed. It's
But
problem.
not all numbers are rational numbers.
Yes, not all real numbers are rational numbers. Any problem with that?
Pi. How
Pi
come?
is a real number.
Okay.
Pi is not a rational number. Actually, real number is the union of rational numbers and irrational numbers. Okay?
Okay.
There are uncountable, infinitely many real numbers that are not rational numbers. They are the irrational numbers. Between any two rational numbers, there is an infinitely many irrational numbers. Okay?
Okay.
Should it clear?
No.
Mi ò gbọ́, kò clear.
Clear.
Okay, what I'm saying is, for all rational numbers, you see, what are rational numbers? Rational numbers are numbers that can be written as A over B, where A and B are in Z, and B is not equal to Z. That's how we define rational numbers. Okay?
Yes, sir.
So, real numbers is like an extension of rational numbers. So we add irrational numbers to real numbers. So there are a lot of numbers that cannot be written as A over B. An example is pi. Pi cannot be written as A over B. Okay? Root 2 cannot be written as A over B. Euler constant cannot be written as a quotient. Okay? So there are a lot of them. So this guy, they are real numbers, but they are not rational numbers. So yeah. They are real numbers. 2 is a real number, but it is not a rational number. Root 7, root 5. Okay? Do you understand? Okay. So that is why R star is not a because 0 does not have an index. Good. So that takes us to the next one, which is about
but if we have like a non-zero number,
if we have what?
non-zero
Exactly, that is a group. So if I remove 0 from R, so R minus 0 together with multiplication, this is a group. So if we remove the Ijiworo cutting down from the set, it will be a group.
Okay.
So to end. Good. Okay. Any other question?
No, sir.
So only time copy. So visible CML.
Sure.
Can you see the remaining time?
No.
Okay. Or Oluwaman retiming. I think she's because she's using the laptop. Okay, 4 minutes. I think we can restart. They are still eating. So we can still do a few more minutes. Okay, so for fundamental theorem of arithmetic, it's one of the basic theorems in mathematics. It tells us that every integer greater than 1, okay, every integer greater than 1 can be written uniquely as a product of its prime factors. Uniquely. So no two integer can have the same prime factorization. Are you following? So if I have 60, that can be written as 2 squared times 3 times 5. So give me any number, no matter how big it is, okay, it can be written uniquely as a product of its prime factors. Even if I scramble it, 3 times 2 times 5 times 2, it is still talking about the same number. Okay. So some other versions will say every number greater than 1 is either prime or composite. So what is the meaning of a composite number?
A non-prime number.
A number that can be written as a product of 2 primes. Okay, a number that is not prime, you are right. So composite means I can break it down. Okay, so every number greater than 1 is either prime or composite. And if it is composite, then it means that we can write it uniquely as a product of prime numbers. Okay, of its prime factors. I want prime, so might be what are the prime factors of 60 kilograms? What are the prime factors of 60?
2, 3, and 5.
3, 2, 3, and 5. Okay, but if I say what is the prime factorization, or what is the express 60 as a product of its prime factor, I want you to write 2 squared times 3 times 5. Okay, so that is the fundamental theorem of arithmetic. So we have fundamental theorem of arithmetic, we have fundamental theorem of calculus, but the one that concerns you, the fundamental theorem of arithmetic. Okay.
Okay, sir.
Then 1 minute. So absolute value. This is not the first time you are coming across absolute value, or is it?
No, sir.
Okay, so we already know what absolute value is. So we need the conclusion of multiply. Okay. So it is important to know that A is always less than or equal to absolute value of A. That's a very important characteristic. So if A is positive, then A will be equal to absolute value of A. But if A is negative, A will be less than absolute value. Okay. So when we come back after the break, come and close in 40 minutes ago, we'll talk about this proposition. Okay. Once it stops, you join again. Good to hear.
Yes, sir. Yes, sir.